taking it today, we'll just take it in the regular room. There's probably enough people not taking it today that we should be able to all fit in there. The next test in here will be next Thursday. It'll be on Chapter 9. So at the end of class on Friday, we were talking about, I was trying to prove something, and then I realized I wasn't going the right direction, so I said, let's stop. And Evan pointed out correctly what I was doing wrong. So what I was trying to do was to prove Euler's identity, which is e to the I pi is -1. And so I'm just going to show you how you get to that. So we've used these three series expansions for e to the x and the sine of x and the cosine of x. In this case, I've substituted theta for x, because most of the time when we're dealing with trig functions, we're dealing with theta. So for both sine of x, put in theta. So I get theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. And it's an alternating series, and each, the square term, the 1 and the square term aren't in here, but the 1 and the square term are in there. They're opposites. And then if you take e to the x power, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So if you have e to the I theta, not e to the I pi, but e to the I theta, and you plug that in, you'll get 1 plus I theta instead of x, and I theta squared instead of x squared divided by 2 factorial. So if we multiply out the top expression, the first term and the second term stay unchanged, but the third term, I squared is -1, so this becomes negative theta squared over 2 factorial, and I cubed is negative I, so this becomes negative I theta cubed over 3 factorial. I to the 4th is I squared squared. I squared is -1, so it becomes plus. So it's plus theta to the 4th over 4 factorial. So if you look down here, I've got 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. And here I have I theta minus I theta cubed over 3 factorial. Here I've got theta minus theta cubed over 3 factorial. So what you can say is that e to the I theta is equal to this term, which is the every other term here, which is the cosine of theta, plus I times the sine of theta. So if I take this and I multiply each term by I, so if I say I sine theta is going to be I theta minus I theta cubed over 3 factorial plus I theta to the 5th over 5 factorial. So you see those are these terms. So you get this result. And then if you let theta equal pi, then you get e to the I pi is equal to the cosine of pi plus I times the sine of pi. And the cosine of pi is -1, and the sine of pi is 0, and so you get that result. So that's called Euler's identity. Now Euler somehow figured all this stuff out before infinite series were invented or discovered. I don't know exactly how he did it, and I'm not a math historian, but the interesting thing is, if you take a class in differential equations, you'll find out that if you want to solve a differential equation that involves e to the, I'm trying to remember how this goes. It's been a while. Anyway, you can solve you do some kind of transformation using something like this, and you end up solving the problem. You have a real integral and you have a integral involving the imaginary part, and you go through the whole process with both real and imaginary parts and how they interact with each other, and then when you get to the solution, you only take the real part of the solution, and that gives you the solution to the differential equation. So that's just one example of where these kinds of this thing that might just seem like an interesting ditty or whatever you want to call it is actually somewhat useful in higher level math. Okay, so that was Euler's identity. So what we're doing last time, to remind you, is we're looking at the convergence of power series. And we'll just go through this one quickly just to show you what we're doing the other day. So what you do is you use the ratio test. So you take the original series that's inside the summation sign, which is this, and you call that u sub n, not a sub n, but u sub n. And the reason is because we have x to the n in this expression. And then you add 1 to all the n's in the previous expression. You'd use the ratio test, which says that this thing converges if the ratio of u sub n plus 1 over u sub n is less than 1. And you go through and you take the reciprocal and group the terms that are like. You simplify it. If you have -1 because of the absolute value, you can just drop that. A lot of times you'll have n over n plus 1 or n squared over n squared, something just involving the ratio of n squareds, and you can use stuff out of section 3, section 3.5, when we looked at limits. Is in that case x goes to infinity, but the same thing applies here for n. And once you end up with this inequality, then you can create instead of using an absolute value, you can take the absolute value away and take this number and just say it's the actual x is between +1 and -1. If this were a half, then you'd be between -1/2 and +1/2. And this gives you the interval of convergence, except because this is only true for less than 1, the question is what happens when it equals the endpoint. So you have to go through and use whatever test is appropriate at the endpoints, which I think must be somewhere. Maybe let me delete these pages because I'm not sure I did it. I think this is the next page. Yeah. So the two endpoints were -1 and 1. And if x was equal to -1 in this case, it's simplified down to this series, which we said diverges because it's a p-series. And the other endpoint, x equals 1, simplified it down. It ended up being an alternating series, which did converge. So this endpoint, -1, didn't converge, and the +1 endpoint did converge. So we put changed this to that, and that stayed the same. And we ended up with that as our interval of convergence. And the radius of convergence was 1. So I handed out, we have a handout, so we'll work through this one. Make sure it's not the one I've already, don't think it's the one I've already done. Let me see let me just double check. Nope, it's new. Okay, so let me give one to you guys here. So how was your trip?
Oh, it was incredible.
Yeah?
So much fun.
Yeah, you must have been yelling a lot or something.
No.
No, just got a cold. Oh.
Yeah, everyone passed it around. So.
Xavier, do you have a copy or not?
I have one. I'm trying to find it.
Yeah. Do you want me to just give you one? So you don't have to.
Thank you. My binder's
If you find it. You can give me the good one back. So we'll go back one page so you can use this previous example as the guide. We've got a couple of them to work on. Yep. Actually, let's go back to this one. There you go. Okay, so the one we're looking at here is 3x to the n over 2n factorial. So what you're going to do is the first step is to just write down what u sub n is, which is 3x to the n over 2n factorial, and then write out u sub n plus 1. So you're going to substitute n plus 1 for n into that expression. And then you're going to take those two expressions, take the ratio of this to that, this divided by that, and then you will take the reciprocal of this part, group the terms together. That there's really only two terms, so you'll have two ratios that have the same form, and then you want to simplify it. So let's get to that point first. I think you guys can do that. So I'll give you a minute head start, or a couple minutes head start. Did anybody, well, probably nobody. Did anybody go see the middle school Mary Poppins this weekend?
Yep. I heard nothing but good things.
Yes, it was very
they
good.
All spent the night at my house last
Oh, did they? Okay. Yeah, it was very good. Yeah, Sydney did a good job. Some people can sing and some people can't, but that's but they all tried hard. Martha and I both made the same comment about somebody that had, I don't know if surprisingly, whoever played the person that sells the flowers, the flower lady.
Yeah.
She had a really good voice.
That's Lydia Armentrout.
Yeah. Yeah. She sounded good. I mean, there were other people that sounded good too, but what I'm going to do is do it right to the right of these. So the only tricky part here, I mean, this one we've done before. The first one is just going to be 3x to the, just 3x to the first power. So see if you can simplify that down. You'll need to multiply out the denominator and then expand the denominator so that you can cancel out the 2n factorial ultimately. So how many people know what that is? To simplified it down. What is it?
2n plus 2 parentheses 2n plus 1 and then 2n factorial.
Right. Yeah. Okay. So when you multiply it out, you get 2n plus 2 factorial. So you start at 2n plus 2, as Daniel said. So it's going to be it'll be 2n plus 2 factorial, and then you expand the denominator out, so it's going to be 2n plus 2, and then you subtract 1 from that, which is 2n plus 1, and then you subtract 1 from that, which is 2n, and then you stop. So 2n plus 2 factorial is, you know, anything factorial is going to be take the first number and subtract 1, multiply it by that, and subtract 1, multiply it by that, and subtract. So that's what we normally do with factorials. So that's what we're doing here. Subtract 1 from 2, you get 1. Subtract 1 from 1, you get 0. At that point, you can simplify it out. And then you can multiply that out if you want to. 4n squared plus 8n. Is that right? No, it's not 8n. So you get 4 plus 2, 6. 6n. So 4n plus 2n is 6n, then plus 2. So that's what we put in here. So we're going to have 1 over 4n squared plus 6n plus 2. So when we take the limit, the first term's unaffected because it doesn't involve n. So Jacob, what is the limit of that as n goes to infinity? What's n infinity squared? Yeah, what's 1 over infinity? 0. Yeah. So the answer is 0. Okay. So what happens then is basically when you take the limit, the first term doesn't change, so that just becomes 3x times 0 is less than 1. So what that implies is that 3x times 0 is less than 1 always, meaning for all x. Doesn't matter what x is. X is going to be multiplied by 0, except for infinity, but we're not worried about that. So any number less than infinity multiplied by 0 is going to be 0, which is going to be less than 1. So our interval of convergence is going to be negative infinity. So anytime the left-hand side becomes 0, and it usually happens because of something like this, then the interval of convergence is all real numbers. And we don't have to worry about the endpoints because nothing ever equals infinity. And the series that we used earlier, the e to the x and sine of x and the cosine of x, those involve all of those have factorials in their denominator. as does this example. So typically, if your original series involves usually, not always. Okay, there are some exceptions to that, but a lot of times, if there's a factorial involved, well, because the Taylor series and the Maclaurin series have factorials. So you think of, well, isn't that all the time? Well, it turns out not. There are some cases where it doesn't end up being in the final formula, but in this case it does. So that's okay. So let's go to the next page. So this is an alternating series. It doesn't involve a factorial in the denominator, but it does involve powers, both where n is the exponent. Actually, n is the exponent in both cases, which is okay. So basically we're going to do the same thing. We'll start with this. You've already got written down. So this is x to the n over 4 to the n. So we'll let u sub n equal -1 to the n plus 1 times x to the n, 4 to the n. And then you'll substitute in n plus 1 for n. Go through the same procedure. In this case, I don't think it's going to be good for all real numbers. So we will have some interval. You might even have some guess at what it should be. Does anybody want to guess what it is? What values of x is this expression going to be converge for? We'll work through the whole thing, but just thinking about it, you've got x to the n, 4 to the n. If you take the ratio of those two, you'll have a geometric series, but you'll have an alternating series. And so as long as x is less than 4, that fraction is going to be less than 1, and therefore the ratio or the limit of a sub n as n goes to infinity should be equal to 0. So I think it's going to be -4 to +4. I'm not sure about the endpoints, but anyway, we'll see what happens. We'll go through the whole procedure, but that's what I would look at it, having looked at them now for 7 years or whatever it is. First year we didn't cover this. First and second year we didn't cover this. So Martha and I watched a movie last night called Gifted. Anybody watch that? Yeah, that was nice.
Went and saw it in the theaters.
Oh, you saw it in theaters? Oh, okay, yeah. That was good. Excuse me. So the well, for Margaret's benefit, the Navier-Stokes equations, that's what the person was trying to solve in the person that committed suicide. The mother, she was trying to solve the Navier-Stokes equations. So the Navier-Stokes equations are the differential equations which govern the flow of fluids. So you take they're the supposedly they take all the terms involved without any simplifications, and then you try to. I'm not sure what they were solving it for, because usually you solve it for a particular what you would call boundary conditions. What's the pressure, temperature, and then usually you can't solve them because anytime you have flow that's not that has any turbulence to it, it gets so complicated you can't solve it. So I don't know how realistic that was. I have to look at it because they're talking about those 7 problems, that whatever it was, the 7 problems challenge problems that nobody'd solved. I have to check on that too. I always like to do a little research after. I was thinking a 7-year-old, could they do some of that stuff that she did? It's a movie, I know. I shouldn't be picking it to pieces. It was good though. Which, I sent you that. I don't know how many people read that article about. Read that article I sent to you, and the reason I sent it to you was, the guy was from Hong Kong, and their feelings of, Hong Kong is an English colony, was an English colony at some point, and my family was kind of, not that they came from, what would be the word? Would be not demonstrative in their emotions. Now Martha's a hugger. If anybody knows her, right? She likes to hug people. I like to hug Martha. She's my wife, but I'm not. When it comes to other people, I'm not so. So, so you plug in your values for u sub n plus 1 and u sub n, and you simplify it down to that. You get -1 raised to the first power, which is -1. And so you take the absolute value of -1, it's just irrelevant. So you just end up with this. So you get the absolute value of x over 4 has to be less than 1. So you can either do it in this step or the next step. You can multiply by 4 before you take the limit, or you can, well, actually, we already did take the limit. So I could do this. I could say x over 4 is between -1 and +1. And then if you multiply everything by 4, you get that. So that's my interval convergence, which is what I thought it was going to be. Now you have to check the endpoints. So what you need to do is substitute in x equals -4 and x equals +4 into the original series. So that's going to be the summation from n equals 1 to infinity of -1 to the n minus 1 power times -4 divided by 4. So this is raised to the n power, and this is raised to the n power. And then if you do it this way, you get summation from n equals 1 to infinity of -1 to the n minus 1, is n plus 1, sorry. And then you have +4 to the n over +4 to the n. So this one just cancels out. Here you just have the summation from n equals 1 to infinity of -1 to the n plus 1 times 1. And over here, you'd have summation from n equals 1 to infinity of -1 to the n plus 1. What happens here is you can rewrite that as -1 to the n times 4 to the n. So when you multiply these together, if you have the same exponent, you can multiply those together and you get -4 to the n. So you can break those things apart. It's like let me just demonstrate that with some numbers. If you have 2 times 4 to the n power, or cubed, that's going to be equal to 2 cubed times 4 cubed. So that's what I'm doing here. Really what I'm doing is I'm taking -4 and making that equal to -1 times -4, both raised to the n power. So, and that's what I've always found the easiest way to deal with that. So then you'll have, now you have the same base, so you can add the exponents. So you'd have -1 to the n plus 1 plus n, which is 2n plus 1 times 1. And over here we have same thing. We don't change it any. So this is always odd. So this is not an alternating series. Actually, it's just summation of -1 times 1 from n equals 1 to infinity. And this is an alternating series with a sub n equal to 1. So you have to look at the convergence. Well, the convergence of this thing, it's just going to be -1 plus +1 plus -1 plus +1 plus -1 plus, it's just going to bounce back. It's going to bounce between, I guess, -1. No, actually, it's not. It's just -1. So this would be -1 added an infinite number of times. So this is going to be -infinity. So this is diverges. Just from you can think of it from the nth term test. A sub n is -1. And unless a sub n goes to 0, then it diverges. So we could say this diverges according to the convergence criteria for the nth term test. And this one is an alternating series, but a sub n does not go to 0 there either. So you could either say it doesn't satisfy the convergence criteria for the alternating series test, or you could just say it doesn't satisfy the criteria for the nth term test. So both of these would diverge at the end. So let me just write that out. So we'll say both endpoints diverge because, so let's a sub n here is just -1. Over here, a sub n is equal to 1. Okay, both endpoints diverge because they fail to meet the nth term test, which says if the limit of a sub n as n goes to infinity does not equal 0, then the series diverges. So our original interval of convergence remains unchanged. So that is our interval of convergence. And you can kind of think of it again. If I let x equal -4, this ratio becomes 1, and we found that for geometric series, it kind of looks like a geometric series that R, the common ratio, has to be less than 1. If it's equal to or greater than 1, then it diverges. Okay, let me pull back here to if you want to write that down. So both ends diverge because they fail, not the fail to meet the nth term test, which says if the limit of a sub n as n goes to infinity does not equal 0, then the series diverges. Okay, moving on. That's pretty exciting. Okay. So the next series is the summation from n equals 0 to infinity of x minus 2 to the n plus 1 divided by n plus 1 times 4 to the n plus 1. So give it a try.
Can you scroll down on the other side?
Yep. Just seeing where you are. Margaret, did you ever have a chance to ask Mr. Graham about Mr. Appel?
I have not.
Okay. I think there is a reception this afternoon that's just a general college reception.
I'll ask him tomorrow.
Yeah, so let me tell you when, if anybody's interested in stopping by to say hello or say good luck. Okay. Actually, yeah, it's when you're still in school. 2:15 today. So the answer, I got -2 to 6. So you take the ratio of u sub n plus 1 over u sub n, and then take the reciprocal of this, group the terms together that match up, and you see x minus 2 to the first power is in the numerator after canceling out, simplifying that term, and 4 just ends at 1 over 4. And the limit of the n part just goes to 1 as n goes to infinity. So you're just left with this. So then you rewrite the absolute value inequality as this range of numbers, -1 to +1, multiply both sides by 4, add 2 to every element in the inequality to solve for x. So you get that. So that's the radius of convergence is 4, because you go plus or minus 4 from the center being at x equals 2. So you go 2 minus 4 and 2 plus 4. So the radius of convergence, let's just write that down. So the radius of convergence is 4, because the original series was centered around x equals 2. We have to check the endpoints, so we're going to plug in x equals -2. So x equals -2, plug that into your original expression, so you'll have -2 minus 2 raised to the n plus 1 divided by n plus 1 times 4 to the n plus 1. And you also do x equals 6. So when you have x equals 6, you'll have the original expression will become 6 minus 2 raised to the n plus 1 power divided by 4. I forgot the n plus 1 part here. N plus 1, 4 to the n plus 1. So you get -4 to the n plus 1 divided by n plus 1. 4 to the n plus 1. And you can, what you can do is you factor out the -1 again. So you get -1 to the n plus 1 times 4 to the n plus 1. So that's the numerator. Still have n plus 1, and you have 4 to the n plus 1. So these cancel out. So you get -1 to the n plus 1 times 1 over n plus 1. Now over here, when you have the positive one, the positive, or the upper limit, you'll end up with 4 to the n plus 1 over 4 to the n plus 1, and then you'll have 1 over n plus 1. So these cancel out without having a negative sign come into it. So one of them ends up being an alternating series, and one of them ends up being not an alternating series. Okay. And we've looked at these before, so I'm not going to write out all the details, but this is an alternating series. It doesn't matter whether this is n or n plus 1 or n minus 1, as long as you have -1 raised to some power involving n. This is going to bounce back and forth between positive and -1. And the two convergence criteria for an alternating series is that this term, a sub n, goes to 0 as n goes to infinity, which it does, and that a sub n plus 1 is always less than a sub n, which it is. So this satisfies the convergence criteria for the alternating series, whereas this is not an alternating series. You'd have to end up using either the direct comparison test or the limit comparison test. We've done that one before. Direct comparison test, you would look at the convergence of 1 over n, actually in both cases. 1 over n is a p-series with p equal to 1, so this would, the one you're comparing it with, 1 over n, would not converge, it would diverge. And because 1 over n doesn't converge, then this doesn't converge or diverges. So this diverges either according to the limit comparison test or the direct comparison test. This one converges according to the alternating series test. So I'll write at least that much down. So this converges alternating series. I'll just go ahead and write them out. The limit as n goes to infinity of a sub n equals 0. And the other requirement is that a sub n plus 1 is less than a sub n. So both of those are true, so, and it's an alternating series, so it converges. This one, you would use either the direct comparison test or the limit comparison test. You could also do the integral test if you wanted to. You know, there's all three of these integral test. All three of these tests would come to the same conclusion, that it diverges. And as a consequence, the original interval, which was from -2 to +6, it turns out it works at -2, but it doesn't work at +6. So you would add that additional equality to make that work. Okay, I'm going to assign the homework for this section, which I don't think I've done yet. So there's your homework for section 8, due next Monday. As far as the physics test is concerned, I'm going to, well, I just found that Asia's not going to be here, and I know you guys are not going to take it. You're going to take it tomorrow, and Xavier's going to take it tomorrow. So we definitely have enough space in the main, just in the physics lab. So I will hand them. Actually, I'll just leave them on the table up front. You can take them whenever you are ready to start. And you have till 10:30. And I guess tomorrow, if you can hand in your the other handout that we never handed in, so the one with all those different tests, make sure you have it done for tomorrow.